Hi, welcome back. So this is lecture 48 in this course on Bayesian modeling. The topic of this lecture is expected log predictive density of a model. We call it ELPD. Okay? We also measure expected log pointwise predictive density of the model. Similar concepts I will explain. So this is actually the measure that we use to evaluate the predictive accuracy of a model. Okay, so if you remember from the previous lecture, we started with this question that how do we measure predictive accuracy of a model? Okay, and we are interested in measuring predictive accuracy of a model on some unseen data or on future data, right? So how do we measure predictive accuracy of a model? Okay, so ELPD is actually one of the metric that we use to measure predictive accuracy of a model. So it's called expected log predictive density of the model. Okay, and you will see that this measure would emerge from exactly the idea that we were discussing in the previous lecture. Okay, so what I'm going to do in this lecture, I will build on where we left in the previous lecture, and then we will work out the exact metric that we can use to evaluate how good is the model's predictive accuracy given some data. Okay, so if you remember how we started our previous lecture, we started with the question of how to measure predictive accuracy of a model given some future data. So let's say you want to measure predictive accuracy of your model on some future data y new. Okay, so this is some future data. Now y new can have multiple data points, by the way. So you can have y new 1, y new 2, right, y new 3. Okay, these are multiple data points in your data set y new. So let's say y new n. Okay, so this is your future data. Okay, but you already have trained your model on some data y obs. So this is the current data you have, which you use to estimate your model parameters. And let's say these data points are y obs 1, y obs 2, and so on, right? Y obs n, right? And the model that we have at that we want to evaluate is, let's say, some model M1 with parameter theta. Okay, so what we are going to do, we are going to train the model using this data y obs. Okay, and then we are going to test how good is the model at predicting this future data y new. Okay, that's our goal. Okay, and you know that we cannot actually have an absolute measure of how good is our model at predicting future data. We always compare it against a candidate model, right? So we cannot have an absolute measure of predictive accuracy of a model. We will always have a measure of relative predictive accuracy of a model. So how good is your model relative to some other candidate model or some other baseline model or other, let's say, a model that makes different set of predictions. So let's say the opposite, the candidate, the competing model is, let's say, M2 phi. Okay, so we are going to measure predictive accuracy of this model and see which one is better at predicting future data, right? So the measure that we are actually going to compute will be ELPD. So we will compute ELPD of model M1, and so this will be an estimate of ELPD. We are not going to compute exact ELPD, but this will always be an estimate of ELPD. In the same way as we obtain parameter estimates, not the exact parameter values. Similarly, you will calculate ELPD for model M2. So that's why I'm representing it by hat, because it's the estimate of expected log predictive density, right? So their difference will actually tell you how good is model M1 compared to model M2 in terms of its predictive accuracy, right? So let us delve into it, that how do we get this measure ELPD and what does it mean? So we are going to build on what we discussed in the previous lecture. So let's say this is your task. You have some data y obs, okay, and you want to predict some future data y nu. Okay, and these are your models that you want to evaluate, M1 and M2. In the previous lecture, I think we called them P and Q, right? So let us call them model P and model Q. Okay, this is fine. Yeah. Oh, sorry, Q and R. I think we called them Q and R in the previous lecture. So let's say this is model Q, this is model R. Okay. Now, the perspective that we took in the previous lecture was that predictive accuracy is actually reduction in uncertainty. And what it would mean for this, for our case, for example, here, it would mean that how much uncertainty is reduced by learning information from this future data. So your model based on, so model is trained on y-obs, right? So let's say this model Q is already trained on y-obs. So let us write it like this. So this is a model trained on y-obs. So this model will generate some predictions. Let us call them posterior predictions after the model is trained on y-obs, right? So if you compare these posterior predictions against this new data, against future data y nu, okay, then how much uncertainty is reduced in whatever the model predicts, right? So that will be our measure of predictive accuracy, right? So in a way, what are we trying to say is that we are going to evaluate that how far are these models posterior predictions from this future data y nu, right? So if the future data looks really, let's say, looks very different from model's posterior predictions, then we would say that model has low predictive accuracy, otherwise it has higher predictive accuracy. Okay? So that's the idea. But how do we measure this reduction in uncertainty? So the measurement that we use was KL divergence. So let's say you want to measure how much uncertainty is reduced when you try to predict a distribution P using a distribution Q. Okay, so that is given by, so both, let's say, P and Q are some probability mass functions, some probability distributions with some associated probability mass function. So this is given by summation of Pi log Pi minus summation of Pi log Qi. Okay, so that is KL divergence from Q to P, right? So you use probabilities from distribution Q to predict the distribution P. Okay, so you can predict the distribution P with this much certainty, right? So basically, this gives you a measure of how well you can predict P using probabilities from Q. Okay, so this is a measure of actually how far is your distribution Q from distribution P. Okay, now what is P and Q here? So Q is actually your model. So Q of theta. So we are talking about this model, right? So when we say these, when we talk about these probabilities Qi's, right? Q1, Q2, Q3, okay? These are actually predictive densities, okay? So I will explain later what that would exactly mean, but they are actually similar to likelihoods, right? So likelihood for different values of theta, right? Given new data, not given old data, but given new data. So for example, let's say your likelihood, let's say your new data is assumed to come from Q of theta, right? Then you can compute the likelihood for each particular value of theta, let's say theta j, given this new data y nu. Okay, so this theta j is actually one of this qj, right? So you can call it qj. Okay, so q1, q2, q3 are actually these likelihood of likelihood that a particular value of theta generates this new data, right? But only thing is that these theta j, okay, actually come from the posterior distribution of theta given the observed data, right? So the model is already trained on observed data. So you sample values of theta from the posterior distribution, and basically for all those values of theta, you calculate predictive density of the model. So this likelihood now will give you predictive density of the model. Okay. All right. We will come back to this later. So these Q1, Q2, Q3 are actually coming from your model Q. So these are predictive density of the model for the new data, right? So how well, with what probability the model predicts the future data, right? So this is fine. But what are these PIs? So PIs here are actually the true distribution of data. They represent true distribution of data. What does it mean? So there is some true target generative process where you want to reach, right? And when I'm calculating this KL divergence from Q to P, what I'm doing here, I'm trying to compute how much is the distance between the model Q and the true distribution. So let's say this is your model Q. Okay. Let's say this is your model Q and this is the true distribution P. Okay. So using this KL divergence from Q to P, I'm trying to compute how far is the true generative process from the model Q. And if you can compute this, this will tell us, well, how far is this model Q from the true generative process, right? So you can directly evaluate whether model Q is a good model or not. Okay. But the problem here is that you do not know what is the true distribution of the data, right? So you do not really know these probabilities P1, P2, P3, right? So you do not have access to this. That's why you cannot directly compute the scale divergence between Q and P. So what you can do instead is that you compute the same. You try to compute the same for another model R, which was basically our competing model. So you compute KL divergence from R to P. Okay. So you do the same for model R. Now you can actually compute a relative KL divergence, right? So relatively, how far is model Q from the truth compared to model R? So what we are all interested in just figuring out whether model Q is far from the true distribution or model R, or in other words, which model is closer to the true distribution P. Okay, that's all we are interested in. And that can be achieved using this. How? So we can actually compute this relative distance from Q to P by subtracting KL divergence from R to P, right? So this will give us a relative distance of model Q. So how close is model Q to the truth compared to some model R, right? So in formula, it would look like this: Pi log Pi minus Pi log Qi minus Pi log Pi minus Pi log Ri. Okay, it will look something like this. Now, interestingly, this term will cancel out. So Pi log Pi term will cancel out. So only term that will remain here is, so what we are trying to do? We are trying to compute relative distance of Q compared to R, right? So what we will have is Pi log Qi plus Pi log Ri. So this is a measure of how far is this model Q relative to R. Okay. So this is actually a metric of distance of model Q from the truth, right? Now interestingly, this term has become symmetric in a way. So for example, when you are measuring KL divergence between P and Q, right? So it was Pi log Pi minus Pi log Qi. So Pi term was in this term as well as in this one, right? So this would imply the distance between Q to P and P to Q, those distances are different. So this is a asymmetric measure of distance between P and Q. But now that is not the case. So the relative distance from P to Q and R to P, so that relatively how close is Q to the truth, this is now symmetric, because it wouldn't matter whether you calculate relative distance, basically how close is Q to the truth or how close is R to the truth, you can use the same formula, right? Because this term will actually give you this whole term including negation, right? This whole term will give you how far is Q, model Q from the truth, and this term will give you how far is basically negative of this, how far is model R from the truth, right? So it actually doesn't matter whether you use this whole thing together or you separately compute this thing for model Q, okay, and this thing for model R, okay, and then take their difference. It would give you same thing, right? So you do not need to compute this entire thing at the same time, you can compute them separately, and they are meaningful for each of these models, right? So this thing actually gives you how close is your model to R, how close is model Q, oh sorry, how far, because this gives you distance, right? So in a way this gives you distance between Q and P. So it's actually relative distance, right? So because it's relative to R, so it's not absolute distance, and this gives you a measure of distance between R and P, okay. Now if this negative term gives you distance, so this distance needs to be minimized if model is closer to the truth. If Q is close to P, then this distance will be minimized. So that means what we can use as a metric of closeness to the true distribution can be given by negation of this, negative log Pi log Qi. If you take negative of this, so this would become summation Pi log Qi. So this will actually give you how close is this model Q to the truth. Similarly, you can compute how close is model R to the truth. So this is a metric of their relative closeness, and then you can take their difference, okay. So this is what we are going to use as a metric of predictive accuracy of a model. So if model Q is really good at predicting future data or at predicting true distribution of data, then this metric, this value should be large, right? So larger this value, then closer is the model to the true generative process, right? So we want to maximize this quantity and we want to minimize this quantity, because this was distance. So we want to minimize distance and we want to maximize this closeness, right? So this is what we are going to use as a measure of predictive accuracy. So now we have arrived at this particular measure of predictive accuracy. So let's say for model Q, this is given by summation Pi log Qi, okay. But in practice, you won't have these probabilities being discrete. So it would be in very rare cases where you would have these probabilities, this distribution to be discrete one, to be a probability mass function. In most cases, it would be continuous, right? You would have continuous parameters and all that. So in most cases, this predictive densities of the model will be continuous. So basically, these will predictive densities, not probabilities. And this would also be true distribution will also be continuous. So rather than using this summation term, for continuous case, what will happen is that you will use integration rather than summation. And integration, how? So this is actually true distribution of data. So what you can write is this true distribution of future data y nu. Okay, so this is true distribution of future data y nu. Now this is log of Q. So, this is representing Q is representing the likelihood or predictive density of the model. So, predictive density of observing new data given that the model is trained on some previous data y obs, and we integrate it with respect to dy new. Okay. So, this is actually a metric of predictive accuracy. You can call it log predictive density. Okay. So, let us call it log predictive density, and there is a reason why we call it predictive density. I will explain in a while. But this is a measure of predictive accuracy of the model Q. Similarly, you can compute it for model R in the same way. Py new log R y new given y obs and dy new. Okay. Similarly, you can compute it for model R. Okay. So, this is a metric we are going to use. This is the thing that we are going to use to compute predictive accuracy of a model. Okay. So, but there are two problems in operationalizing this measure of predictive accuracy. One is this integration. I mean, we can't keep doing this integration. This would be, I mean, this function might not be integratable at all, and it might be very difficult to integrate. So, that is one problem. So, we cannot analytically solve this most of the times. Second problem is this, that you don't know what is the true distribution of data. We are using this here, but I don't know what is the true distribution of the data. So, how to deal with these two problems? Okay, how to solve these two problems? Okay. So, there is actually a much simpler solution than you think. So, you know about Monte Carlo integration. I think I taught you briefly how Monte Carlo integration works, right? So, we are going to apply Monte Carlo integration here to solve this problem. How? So, what is happening here is this, that this is some function log of q y new given y obs, right? This is the distribution of some variable y new, and we are integrating this whole thing with respect to this variable y new. Okay. So, you can actually approximate this integration using this. So, this integration can be approximated by log of q y new I given y obs, okay, and this will be average from I1 to n, where n is the number of data points in your future data, right, where y new I comes from true distribution y new. So, you can rewrite this statement like this. So, this term will be an approximation of this integration. This is called Monte Carlo integration. So, this is a general idea, you can apply it to anything. So, whenever you have, let us say, functions like, for example, we use this to calculate expected value for random variable. So, let me take you back to how we calculate expected value for random variable. So, let us say you have a random variable x, f of x is the probability density function of the random variable. How we calculate expected value of the random variable? We calculate it using this integration of x f of x dx, right. Now, we can actually approximate this using Monte Carlo integration as well. How? This f of x is actually a probability distribution, right. So, whenever we are in this situation, when you have a probability distribution, what we can do is that we can sample a lot of values of x, let us say xj, from this, let us say xi, from this distribution f of x, right, from this probability distribution f of x, and for each value xi, we can we can take their average, right? So using like this, the summation of xi from I is equal to 1 to n. So this thing will give me approximate. So let me write it like this. This will give me approximate expected value of the random variable. But there is a condition that this n should be very large, right? So as the number of samples from this distribution will increase, the approximation will become more exact, right? So the same thing, E of x, the expected value of random variable can be approximated like this. So what we all did here, because this was probability distribution of this variable x with respect to what we are integrating here. So you sample this variable, the values of x from this probability distribution, and then plug in those values in the remaining function inside the integration. What is the function inside the integration? Just x, right? So we write xi. Similarly here in our example, in our predictive accuracy metric, what we want to calculate is this integration. So we are given probability distribution of this new data, and then there is some function of this new data, and we are integrating it with respect to new data. So this can be approximated if we draw a lot of samples of y new from this probability distribution P of y new, and then plug in those samples of y new inside this function and take average of the values of this function over a lot of samples, let's say n. Okay, so this will give us a good approximation of this integration, right? So this is actually what we are going to use in practice for calculating predictive accuracy of a model. Why? Because in this we do not need to worry about solving the integration, right? We also don't need to worry about the true distribution of data, because whatever future data you will have, it is already coming from this true distribution y new, right? So assuming whatever data you have, it's already coming from true distribution P of y new, you just have to compute this, right? Because this statement is already ensured, because whatever new data you have, it's coming from the true distribution, right? So we only need to calculate this. This is actually called expected log predictive density, okay, ELPD. Why expected? Whenever we do this Monte Carlo integration, this part basically is called taking average value over large values of this function under repeated sampling from P y new. Okay, this would be called expected value of this log predictive density function, right? So this is expected log predictive density of the model. Okay, so this is what we are going to use as a measure of predictive accuracy. Okay, so let me write it clearly here. So ELPD of model Q, okay, is given by average of log y new I given y obs, right? Sorry, log of q y new I given y obs, right? So this is what we have as formula for ELPD, right? So we can just now estimate ELPD values given a model and some future data y new and given some current data y obs, right? But only thing that we still need to solve is this, that how do we calculate this quantity q of y new given y obs, right? So this looks like something new. Q of y new I given y obs. How do we calculate this? And what is actually this quantity? This quantity is, or this term is actually how well you can predict this future data point y new I, given that the model has already been trained on y obs, right? So basically this compares the posterior distribution or the posterior prediction of the model against this actual observed data point y new I, right? So how do we calculate this? So this is actually, in a way, you are trying to calculate likelihood of observing this new data point y nu I given some particular parameter values such that those parameter values are coming from posterior distribution of the model when model is trained on y orbs, right. So, there is a way to calculate this. What we can do, we can integrate basically likelihood of observing y nu I given some sample theta, okay, given parameter theta, right, and such that theta is coming from posterior distribution when model is trained on y orbs with respect to d theta. Okay. So, this term is actually this. So, this is marginal likelihood of observing this new data point y nu I given that the model is trained on y orbs, right. So, it is actually marginal likelihood of observing this new data point given the model, okay, in a way given the model which is trained on y orbs, right. So, you can write it in this way, right. Now, of course, the integration will be difficult here as well. So, what you can do instead is that you can again compute this using Monte Carlo integration. So, basically you can compute average, let us say 1 by n summation j is equals to 1 to n, okay, q of y nu I given theta j. So, theta j is a sample from the posterior distribution of the model. So, I will write it as p hat. Let me write p hat. So, p hat means this posterior distribution is estimated using y orbs, right. Okay. So, you can estimate this using this basically expected likelihood or expected predictive density of the expected predictive density of observing this new data point y nu I given samples from the posterior distribution of theta. This is what it means. Okay. So, this I have calculated for a single data point. Okay. This is also called point. So, basically this is predictive density for a particular data point y nu I. So, similarly you calculate this predictive densities over multiple data points, right. So, actually this measure, then if you have multiple data points in your future data, would then be called ELPPD. Actually it is called ELPD, but you can call it expected log pointwise predictive density, which means that we are calculating these expected log predictive densities over multiple data points. So, your future data has multiple data points, right. Okay. So, this is the way we are going to compute this, right. So, this is the whole formula of ELPD, right. It looks complicated, but the only thing you need to do is this, that first let's go from bottom to top here, right. So, first estimate posterior distribution of theta given observed data y orbs. Now, draw samples from this posterior distribution for theta, and conditional on each sample from the posterior you calculate predictive density of observing a new data point y nu I, right. So, this will give you predictive density of y nu I. We plug in predictive density here, take log predictive density and take its summation across all data points in your future data y nu. Okay. So, this is the process, right. This is ELPD of any model Q. So, I can write the whole formula here. So, let us say ELPD of any model Q is given by expected log predictive density over multiple data points y nu I given that the model is trained on y orbs, where q y nu I given y orbs is actually expected capital N, j equals to 1 to n, q of y nu I given theta j, right, such that theta j comes from estimated posterior distribution of theta conditional on observed data. Okay. So, this is the entire formula for ELPD. Here you do not need to worry about this statement that y nu I comes from P of y nu, because it is always going to come from P of y nu. Okay. So, you do not need to worry about that. So, we can leave it, because each y nu is already coming from the true distribution. So, you do not need to generate y nu, this is already generated from true distribution, right. All right. So, this is it on expected log predictive density of a model. So, we are going to use this metric to compute predictive accuracy of a model compared to some other candidate model, right. All right. So, I will stop here. In the next lecture, we will discuss cross validation, okay, which is a method where we use this ELPD metric to compare competing models, right. All right. I will stop here. Thank you.